Hello students, Jai Hind. Welcome to my YouTube channel. In the previous session, what we have discussed was Kirchhoff's laws. The first rule, it's known as the junction rule, which is based on the law of conservation of charge. It states that the sum of the currents entering a junction is exactly equal to the sum of the currents leaving that particular junction. And the second rule to it, it is applicable for any closed part of an electrical network. And that is known as the loop rule, right? And as per the loop rule, the algebraic sum of the EMFs is equal to the algebraic sum of the products of the resistances and the currents flowing through them. And we have also discussed the sign convention to be used over here, right? So let's practice using those rules in solving these complicated circuits, right? So these are the 4 questions which we'll be attempting to find using Kirchhoff's laws, right? First question, please concentrate this first question. It's a skeleton cube. It is a skeleton cube made up of 12 identical wires, each of same length and each offering resistance smaller, right? You are supposed to find out the net effective resistance between the 2 points which are diagonally opposite to each other. Here A and B are the 2 points which are diagonally opposite to each other, right? So in each of these cases, what we are supposed to do is, we are supposed to find out the effective resistance between the points A and B. In the first case, the 2 points A and B are diagonally opposite to each other. So students, let's try the first one. So A and B, these are the 2 points between which the net effective resistance is to be calculated. So what to do is, first step is, let us assume a source to be connected across these 2 points. This is a source, suppose of EMF E, and sending current along this direction. So whatever current is being sent through the positive terminal of this battery, the same current must enter to its negative terminal. That is when the circuit is said to get completed, right? Now consider this particular point, students. It's a symmetrical diagram. And in symmetry, you are aware, the current flowing across each of the symmetrical portions of the mirror image of the 2 parts must be same, isn't it? So what to do is, the current will get equally divided between these 3 branches, right? Net current entering at point A, it will get equally divided between these 3 branches. Why is it so? Because current will enter at point A and will leave at point B. Between A and B, the current will tend to follow least resistive path. So least resistive path is this one, R, 3R. This is R, 3R, and again this path, if the current follows, it will be offered a resistance of 3R. So in all the 3 paths which offer minimum resistance, it is offered resistance of 3R. So the current will get equally divided among these 3 branches. So what to do is, let us consider the net current entering point A is 6I. So it needs to get equally divided amongst these 3 branches. And as per the junction rule, we are aware, net current entering must be exactly equal to the net current coming out from that junction. So it will get equally divided between 3 branches. So it is 2I, this is 2I, and this will be 2I. Now look, this will act as a junction. Here the current entering is 2I, and this is where the current must exit. So these are the 2 paths offering resistance of 2R and 2R. So again, these 2 paths are identical in the sense that they are offering same resistance. So this 2I will again get equally divided between these 2 branches. So 2I will get divided equally, I and I, right? Similarly, this point will act as a junction. Here the current entering is 2I, so it will get equally divided. So 2I will get equally divided between 2 branches. Over here, 2I current is entering at this point, isn't it? So this is the exit point. So this path is offering and this path is offering the same resistance. So again this current 2I will get equally divided, I and I. Right students? Again let's make use of junction rule over here. Here the current entering is I and here the current entering is I. So the net current leaving this junction would be 2I. Similarly, if you consider this particular point, here the current entering is I and here the current entering is I. So the net current entering at this junction is 2I. So leaving net current would be also 2I. Now consider this one, this point. I, these are the two currents entering, so the current leaving this junction will be again 2I. Consider point B, which will act as a junction. 2I, 2I, 2I. Net current entering is 6I. Therefore, the net current coming out of point B must also be 6I. Right? So, point to be noted is that, students, at each and every junction, the junction rule must hold valid. So, due to the symmetry nature of this diagram, the current will get equally divided as we have distributed the current in this particular case. Right? Now, let's try to find out the effective resistance. Now, let's make use of loop rule. You can consider any loop. Let's consider this loop, this loop. Let us consider this loop. So, in this loop, let us consider loop rule. So, using loop rule, what we get is, we are aware algebraic sum of EMF is equal to the algebraic sum of the products of the resistances and the currents flowing through them. So, students, we are considering this particular loop. This is the closed loop I am considering. This loop I am considering, right? And in the clockwise direction. This is the loop I am considering, and that too in the clockwise direction. Throughout this loop, the only EMF is this one. And this cell is sending current in the same direction as that of the measurement of the loop, that is in the clockwise direction. So this EMF is to be taken as positive. No other EMF is included in this loop, right? So now summation of IR. So this is current is flowing along the same direction as that of the measurement of the loop. So here it will be 2IR. Plus here we are dealing with this particular loop. So in this branch the current is again flowing in the same direction as that of the measurement of the loop. So it will be plus IR. Plus consider this branch. Here again current is flowing in the same direction as that of the measurement of the loop, that is in the clockwise direction. So this needs to be taken as positive. So 2IR. So this is the loop we have considered, and in this particular closed part of the electrical network we have made use of loop rule, right? Now students, EMF. EMF is net current multiplied by net resistance between those 2 points where the EMF is applied. What is the net current? Net current flowing through the circuit is 6R. This is the net current. What is the effective resistance between A and B across which this EMF is included? That is RAB. This is to be found. And it is equal to 2IR plus IR plus 2IR. That will give us 5IR. Am I clear, students? So, rearrange the terms. What you get is RAB is equal to 5 by 6R. So this is the solution of the first question. So students, this is how we can make use of junction rule as well as loop rule so as to determine the answer. Right? So this was the case of a skeleton tube made up of 12 identical wires, each offering resistance R. So in such a scenario, the net effective resistance between the 2 points which are diagonally opposite to each other is found to be 5 by 6 times the resistance of each wire. Right, students? Okay, let's consider the next question. Let's consider the second question. First question was relatively simple because of the symmetrical nature of the circuit. Second is same. It's again a skeleton tube made up of 12 identical wires, each offering resistance R. In the previous case, we were supposed to find out the effective resistance between the 2 points which are diagonally opposite. Here, we are supposed to find out the resistance across any one side of the cube, right? A and B are the 2 points. So, as was considered in the previous case, we'll consider a battery or a cell of EMF E to be connected across the points A and B. Clear, students? Okay. Now, just check the diagram. So what to do is, current will enter over here and current will leave at this particular junction. Whatever current is entering at point A, the same current must be leaving from point B. That is when the circuit will get completed. Now look, this path and this path, both are identical. Look, this one and this one, both are identical. So whatever current is flowing along this branch, same current will flow through this branch. same current will flow through these two branches. These two branches, same current will flow. Again, these two branches, the same current will flow. Again, due to symmetry of the diagram, right? So what to do is, and here the current will be different. So what to do is, we can write the current over here is 2I plus I1. Why I have written 2I plus I1? You will fully get convinced. Suppose current I1 flows across this branch, and along these two branches, current will get equally divided. So out of 2I, current I will flow through this particular branch, and another current I will flow through this particular branch. Right, students? So apply junction rule. Net current entering at point A is 2I plus I1. So I and I1. Net current coming out of that junction is also 2I plus I1. These two being symmetrical portions, the current should be flowing same current must be flowing across each of these two portions, right? Now look, over here, suppose current flowing is, this point will act as junction, current I is entering. Suppose current flowing is I2. Now out of I2 flows through this branch. So the remaining current, that is I minus I2, will flow through this branch, isn't it? Now this part is symmetrical to this part. So along this branch, the current flowing must be I2. So out of I2 current flows along this branch. So the remaining current, that is I minus I2, must flow along this branch. Now students, look, I minus I2, I minus I2. So the net effective current over here would be twice I minus I2. So this is the net current which will enter at this point. Now, this is the net current entering at this point, and this is where the current must leave. So these two are the branches which are offering equal resistance. So the current will get equally divided. So 2I minus I2, it will get equally divided, means over here current would be I minus I2, and over here current would be I minus I2. Right? Now this will act as a junction. Here the current coming is I2, here it is I minus I2. So these two currents are entering. So add them. So I2 minus I2 get cancelled, so we'll be left with current I. Similarly, here I minus I2, and here it is I2. So the current leaving from this point would be I. Now look, at this point, current I is entering from this branch, current I is entering from this branch, and current I1 is entering from this branch. So the current leaving through point B would be twice I plus I1. So whatever current is entering this circuit, the same amount of current is leaving through that circuit, right? So applying the junction rule at each and every junction, the junction rule must hold valid. So students, what are the number of variables over here? I, I1 and I2. So there are three variables. So in order to solve this question, we have to construct three equations, right? So let's first consider this one. Consider this loop. This is loop 1. Consider loop 1. Consider loop 1 and in the clockwise direction. Let's make use of the loop rule. So in this closed part of the network, the only EMF is this one, and it will send current along this direction. That is along the same direction as that of the measurement of the loop. So as per the sign convention, the EMF of this cell is to be taken as positive. So it is plus E. Right? No other EMF is included. Then IR, this one. Here current is flowing along the same direction as that of the measurement of the loop. So it will be taken as positive. So it is I1R. Right, students? Okay. Net EMF, it's net current multiplied by net resistance. What is the net current flowing through it? It is 2I plus I1 into what is the effective resistance across which this EMF is connected? It is to be determined, which is RAB. This is to be determined. So net EMF is net current multiplied by effective resistance between those 2 points across which the EMF is connected. I1R. I1R. Put this as equation number 1. So students, we need to find out RAB in terms of small r. So what we intend to do is, we will try to convert I1 in terms of I and substitute the value of I1 over here. So II will get cancelled So RAB may be obtained in terms of small r. So that is the approach which we will follow, right? So this is equation number 1. Let's try another loop. You can consider this loop, the top portion, the upper face. So consider this to be loop 2. Consider this to be loop 2. So consider loop 2. Let's make use of loop rule. The upper face, right? I am taking it in the clockwise direction. There is no EMF. So no EMF means summation E is equal to 0. There is no EMF included in this closed part of the network. And over here, the current is flowing in the same direction across these 3 branches as that of the measurement of the loop. So it will be I minus I2 multiplied by R plus twice I minus I2 multiplied by R plus I minus I2 multiplied by R, right? So these are the 3 branches we have considered, and this one is the 4th branch. I am measuring the loop in the clockwise direction, and in this branch the current is flowing in the opposite direction. So this current I2 is to be taken as negative, so it is minus I2R. So R is common, so that gets cancelled. So 1 time, 2 time, 1 time, 2, 3, 4 times I minus I2 minus I2, isn't it? R is common. So solving, what you get is I2 is equal to 4I minus 4I2. So 4I is equal to 5I2, or I2 is equal to 4 by 5I. Put this as equation number 2. As I told you students earlier, that there are 3 variables. Which are those 3 variables? I, I1 and I2. So in order to solve or get the answer for these 3 variables, we need to construct 3 equations. So we are done with 2 equations. So we need to consider another loop as well. So what we do is, let's consider this one. Let's consider this loop. Let's consider this loop. This is the 3rd one. Right? Let's consider this loop. This involves I2, so I think we should get the result by considering this particular loop. So consider loop 3rd. Again, I have considered it to be measured along the clockwise direction. So again, in this closed part of the electrical network, there is no EMF. So it will be 0. And then let's start from here. So current is flowing in the same direction in these 2 branches as that of the measurement of the loop. So it will be assigned positive sign. So it is IR plus, over here the current flowing is I minus I2. So it is I minus I2 multiplied by R. Now this branch, here the current is flowing along this direction, but the loop is measured in the opposite direction. So students, here current as per convention is to be assigned negative sign. I minus I2 into R. And over here again current is to be measured in the opposite direction. So it is minus IR. Look, if you consider this loop, you will get 0 equals to 0. So we won't reach anywhere. So you have to avoid considering this particular loop. This is valid, but we won't get any equation. So let's consider some other loop. Let us consider, instead of loop 3, let us consider some other loop. So let's check. We can consider this front face. Let's consider this front loop, right? This front part. Or rather, you can consider this part, the back. It should involve I2. So consider this bottom one. Okay, consider this to be 3rd loop. And consider this one, 3rd. So considering loop 3, you have to consider that loop, students, in which we intend to get some relationship between I1 and I2. So let's consider the base part. So again, there is no EMF, so it will be 0. And here in these 3 branches, the current is flowing in the same direction. So what I get is IR plus I2R plus IR. IR plus I2R plus IR. Here current is flowing in the opposite direction. So it is minus I1R. So now we can easily get the result. So what you get is 2I plus I2 minus I1 is equal to 0. Now students, only mathematical steps are left. Right? We have made use of the loop rule so as to obtain these three equations. Now, you can substitute the value of I2 over here. So from second, substitute the value of I2. So what you get is 4 by 5I is equal to I1, isn't it? So that will give you 14 by 5I is equal to I1. So I can be converted in terms of I1. So I is equal to 5 by 14 I1. Okay, now the last step. Now students, the last step. Simply substitute this value of I as 5 by 14I over here, and I1 will tend to get cancelled out. So we'll obtain the result RAB in terms of small r. So let's do the last step. So we simply need to substitute this value of I. We simply need to substitute this value of I in equation 1. So what you get is 2 in place of I, write 5 by 14 I1 plus I1 into RAB is equal to I1R. So what you get is 5 by 7 I1 plus I1 into RAB is equal to I1R. So that will give you 7 plus 5. 12 by 7 I1 RAB is equal to I1R, or net effective resistance between the 2 points across any side of the cube, it will be given by I1 get cancelled, it will be 7 by 12R. So this is the answer, students. So in the first case, the effective resistance between the 2 points which are diagonally opposite, it was 5 by 6R. In case of the same situation but effective resistance across any side of the cube, the answer is 7 by 12R. So students, although the same circuit, but remember between which 2 points the net effective resistance is to be found, right? So we are done with the question number 2. So answer is 7 by 12R. So continuing, let's start with the third question. Third question, student, one of the side is taken out, right? Here it has got 11 wires. One of the wires is taken out. It has got 11 wires. And here we are supposed to find out the net effective resistance between the points A and B. Between the points A and B, right? So we will try to connect a source between these 2 points. This is a source. This is suppose of EMF E, right? Let's distribute the current as was in this case. This circuit and this one, they are identical. Whatever current is flowing through this branch, the same current will flow through this branch. Whatever current will flow through this branch, same current will flow through this branch. So these two are identical. And whatever current is flowing through this branch, same current will flow through this branch. Isn't it, students? So let us consider the net current be 2I. So it will get distributed. So here it will be I, and here in this branch the current would be I. Suppose here the current flowing is I1. So out of I1 current flows through this branch, so that the remaining current I minus I1 will flow across this branch. Okay. Similarly, here the current flowing is I. Its symmetrical part is this one, same current must be flowing I1. So out of I1 current flows over here. So the remaining current I minus I1 will flow through this particular branch. Now consider this point. It will act as a junction. So current I minus I1, here current I minus I1. Both will add up and it will give twice I minus I1. Then again at this point, this is the net current ending at this point, and this is the point where the current will make an exit. So both are offering the same resistive path. So this current will get equally divided. So twice I minus I1 will get equally divided as I minus I1, and over here again I minus I1. This point will act as junction, I minus I1 and here I1. So the net current is I. Here I minus I1 and over here I1 is current. So the net current over here would be I. So look, at this point the current entering is I and this is I. So what is the net current? It is 2I. Simple. So as I told you students, make sure that at each and every junction rule must be obeyed. That is, the sum of the currents entering that junction must be exactly equal to the sum of the currents leaving it. Right? So we have got two variables. What are those variables? I and I1. So we need to construct only two equations. So let's consider this loop. Consider this loop. This one. I am considering this loop. And in this closed part of the electrical network, the EMF is E and will be sending current in the same direction as that of the measurement of the loop. So this EMF is to be taken as positive. So plus E. It is equal to, here the current is I, and in these three branches, the current is flowing along the same direction as that of the measurement of the loop, that is in the clockwise direction. So all the currents are to be assigned positive sign. So here we get IR. Here it is I1R. And over here it is again IR. Now net EMF, it's net current multiplied by net effective resistance. Net current through the circuit is 2I. Net resistance between the points A and B, which is to be found, is considered to be RA, is equal to 2IR plus I1R. Put this as equation 1. So somehow students, if you are able to substitute the value of I1 in terms of I, then I on both the sides will get cancelled out. So RAB can be found in terms of small r. That is to be done now, right? So for that, we need to construct second equation by considering loop rule. So consider any loop. Let's consider this loop in the clockwise direction. So consider loop 2. Using loop rule, what we get is, in the upper face, the closed part of the electrical network, there is no EMF. So net EMF is 0 and it is equal to summation IR. So which will give us I minus I1 into R. This taken as positive, the current. This one will be also positive, this one will be also positive. All are in the clockwise direction. So plus twice I minus I1 into R plus I minus I1 into R, and over here loop is measured in the clockwise direction, but in this branch the current is flowing in the opposite direction. So this current needs to be assigned negative sign, minus I1R. Clear students? Let's solve it. 1 time, 2 time, 1 time. So it will be 4 times I minus I1 into R minus I1R. R, that obviously can't be 0. So what you get is 4 times I minus I1 is equal to I1, or 4I minus 4I1 is equal to I1, or 4I is equal to 5I1. So therefore I1 is equal to 4 by 5I. Put this as equation number 2. Now the last step, students. Substitute this value of I1 as 4 by 5I over here and we should get the result. Right? So from 1 and 2, what do we get is twice I RAB is equal to twice IR plus I1 into R, that is 4 by 5 into I into R. So 2I RAB is equal to 14 by 5 IR. So that will give us 7 by 5 into small r. So this is the effective resistance between the points A and B. So students, you need to practice such questions. Do as many numericals as you can. It is only by practicing that the efficiency can be increased or efficiency. Okay students, now since we have done first question, second question and third question, let's attempt the fourth question. Fourth question students, let me draw the circuit diagram again, right? So this is the base and this each side is of resistance R, like this, right? Each side, it has got a square base, so it's in the form of a pyramid. So this is the diagram basically. So we are supposed to find out the effective resistance between the points A and B. Okay, this is the diagram. The points are A and B. Between these 2 points, the effective resistance needs to be determined. This is point A and this is point B. So what's the technique, students? First step is to connect a source between the 2 points across which the effective resistance is to be determined. So we'll connect a source over here, say of EMF E. Let us consider the EMF to be E, right? Now, net current, suppose it's I, so the net current entering the negative terminal must also be I. Over here, this path is offering resistance R, this path is offering resistance 4R, this path is offering 2R. So current will be different across different branches, isn't it? So in case we consider the current flowing over here is I1, flowing through this branch is I2, then the current across this branch would be I minus I1 plus I2. Correct, students? Apply the junction rule at point A. Net current entering is I. Net current leaving this junction A should also be I. So add these 3 and you should get I. Now look, this part and this part both are symmetrical. So same current must be flowing, and this part they are symmetrical. So same current must be flowing, right? So anyway, this point will act as a junction. Suppose this is current I3. Out of I3 current goes through this branch. So the remaining current, that is I2 minus I3, will be flowing through this branch. Okay. This point will act as junction. The current entering is I1 and I3. As I have told you, these 2 are symmetrical portions and these 2 are symmetrical portions. So, here the current should be I1 and here the current should be I3. Isn't it? Net current entering this junction is I1 plus I3. Net current leaving this junction is I1 plus I3. Clear, students? Okay. Over here. Here the current entering is I3 and through this branch the current entering is I2 minus I3. So add these 2. What we'll get is I2. Current entering is I1 and over here it is I2. And over here I minus I1 plus I2. So add these 3 currents which are entering at point B. On adding these 3, I1 plus I2 plus I minus I1 plus I2, you will get I. So at each and every junction, the junction node is valid. Right? So how many variables are there? I, I1, I2, I3. So students, there are 4 variables. So we need to construct 4 equations, right? Let's start with the first one. Let's consider this loop. This is loop number 1. So for loop 1, let's consider the loop 2. So we are considering this loop in the clockwise direction. Only EMF is E, and this cell will send current in the same direction as that of the measurement of the loop. So as per the sign convention, this EMF is to be assigned positive sign. It is equal to summation of IR. Only resistance is this one. So here the current is flowing in the same direction as that of the measurement of the loop. Therefore, this current is to be taken as positive. So what do you get is I, just open this bracket, minus I1 minus I2 multiplied by small r. This is equation number 1. Right, students? Consider it to be equation number 1. Right? So, we need to consider another 3 equations. Let's do it. Consider the base, the square base of this pyramid. Consider this loop. So, for closed loop 2, let's make use of loop rule. Right? So, in this loop, there is no EMF. So, the net EMF would be 0. And in these 3 branches, the current is flowing in the same direction as that of the measurement of the loop. So in these 3 branches, whatever current is flowing, it should be assigned positive sign. So over here it will be plus I2R. Over here it will be plus I2 minus I3 into R. Over here it will be again plus I2R. And in this branch, loop is measured from B to A, but the current is flowing from A to B. So this current is to be assigned negative sign. So it will be minus I minus I1 minus I2 into R. So students, this is equation number 2. Right? This is the second equation. Third one. Let's consider this one. Let's consider this part involving current I3. Right? So for loop 3, let's apply the loop rule, which is the Kirchhoff's second rule in this particular closed network, right? Again, there is no EMF in this closed part of the electrical network, so net EMF is 0. Over here, I3 and again I3, current is flowing in the same direction as that of the measurement of the loop, so these two currents are to be taken as positive. So I3R again plus I3R. And here the current is flowing in the opposite direction as that of the measurement of the loop. So this current is to be taken as negative. So it is minus I2 minus I3 into R. So this is student equation number 3. Now another equation is required, right? So fourth equation, consider this side, this one. Consider this fourth loop. So for loop 4, again there is no EMF in this closed part of the electrical network, so net EMF is 0 over this loop. And let's start from here. In the same direction, here the current is flowing in this branch in the same direction as that of the measurement of the loop. That is in the clockwise direction. So this is to be taken as positive, I1R. Here in this branch, the current is flowing in the opposite direction. We are measuring the loop along this direction, current is flowing in the opposite direction. So this current I3 is to be taken as negative. And over here again, measurement is in the clockwise direction and here current is in the opposite direction. So here again negative sign is to be assigned. Minus I2R. Put this as equation number 4. So students, there are 4 variables and we have obtained 4 equations by using loop rule. Now I hope the rest of the calculation can be easily done by you. These are the 4 equations which are to be used, and substitute the values of I1 and I2 over here in terms of I, right? And that will give you the answer. In place of E, net EMF is net current multiplied by net resistance. What is the net current? It is I. Net current flowing through the circuit is I. And what is the effective resistance between the points AB? It is RA. It is equal to I minus I1 minus I2 into R. So students, what you need to do is that using the other 3 equations, substitute the value of I1 in terms of I and also substitute the value of I2 in terms of I. So I on both the sides will get cancelled out and you will get the result RAB in terms of small r. I will tell you the answer. The effective resistance in this case is found to be, I think, 8 by 15 times smaller. So please complete this solution by using these 4 equations, right? Hopefully you have understood the concept, and as I told you numerous times, keep practicing more and more such questions. I will devote one more lecture which is based on numericals on Kirchhoff's laws, right? So students, do take care and practice numericals. Thank you.